Shahnaz. In this lecture we will introduce Hom Functor. Now before that, let us do some homework. So if we had two R modules, say A and B, so A and B, they are R modules. Now let us consider the set of all R module homomorphisms from the module A into module B, and let us note that set by Hom AB. So these are this is a set of R module homomorphism. So let us write down R here to make it clear that we are dealing with R module homomorphisms. Then this set has a module structure, an R module structure. Now we know that now we want to see how this module changes when either of the modules A or B is fixed and the other changes. So let us consider a module D. So suppose we have module D here, and suppose phi belongs to AB. Phi is a module homomorphism from A into B. So here we have A and B. So this is the module homomorphism phi. Now this D is any R module. Now if we have a morphism, a module homomorphism, this phi, this induces a module homomorphism phi star from, so this phi induces a module homomorphism phi star from Hom dA to Hom dB. So these are R module homomorphisms. Now this phi, this induces a module homomorphism from this module to this module. So suppose we have a map phi, say map F, sorry, this is map F. Now we have to look at, now suppose F is here, so F is in this set because F is a module homomorphism from D to A. Now this module homomorphism, phi, this induces a morphism from module homomorphism to dB, which is given as, first we operate F, then phi, and let us, for the sake of brevity, let us write this as phi F. Let us note this, define this module homomorphism as when this phi star acts on F, we get this map phi F. Now this F is here, and this phi F, this is in this module. So this phi star is induced by this phi. Similarly, any R module home. Now suppose we have a module homomorphism, suppose psi from B to C. So this is module homomorphism psi, and this is module D. And suppose we are given a module homomorphism from D to B. So this is G. Then this psi induces a module homomorphism psi star from Hom dB to Hom DC. these are R modular homomorphism, because G belongs to this set. So when this psi star acts on G, we get an element here, I mean an R modular homomorphism from D to C, and that is given as psi G. So let us define this psi star as, when psi star acts on G, we get psi G. Now if we take composition of these two modular homomorphism, I mean phi star and psi star, what do we get? Suppose, so we have D here and we have A, B and C, these are our R modules, and here we have phi and this is psi, this is map F, this is G, and this G is actually equal to phi F, and we have map here H, which is equal to psi G. Now this phi star, this carries this map F to this map G, and map psi star just carries out this G to H, such that if we compose these two morphisms, psi star, and so from this what we get, so we have a map like this, A to B, a sequence like this, A to B, B from B to C, we have map phi and we have map psi here. So this sequence of modules and homomorphisms induce this sequence here, hom dA, hom dB, hom dC. So these are the R modules and these are the morphisms. Here we have phi star and psi star. Now if we look at this map, psi star, phi star, if we act this composite map on, say, so phi star acts here on F, because phi star F is phi F. So this is same as psi star of phi star of F. This will be same as psi star, this is phi F, and this is psi phi F, which is same as psi star phi star of, sorry, I mean this is same as psi star psi phi of star. So similarly, given any R modular homomorphism phi from, I mean similarly, given any R modular homomorphism, say phi from A to B, then this phi induces a homomorphism phi star from Hom. Now here these modules, these modules A, B and C, so and this module D is fixed everywhere. So now what we'll do, we'll fix module D at the second place. Now let us see what will happen. So this induces, so now we have D here, A, B and C here. So this is map phi, this is map psi. Now we have modular homomorphisms from A to D, B to D and C to D. Now this phi from A to B, this induces a homomorphism from, so this phi is from A to B. So if we have, suppose G here, suppose we have F here, so this phi star carries this map to here, to some map here. So obviously this map will be F of phi, because going from A to D via B is same as going from A to D directly. So this direct map phi F is same as this F composed with phi. So this phi induces a map from, so this F is a modular homomorphism from B to D. So this is an element of Hom BD, and this phi star takes this map F, which is here, to a map to a modular homomorphism from A to D. So this is from A to D. This is phi star, where this F is carried out to F of phi, i.e. this phi star of F, this is F of phi. And likewise if we have module D here and B to C, we have a module homomorphism, suppose psi, then this psi induces a homomorphism psi star from Hom CD. So it carries out this map G to a map here. So this G is carried out to this map psi G psi, so this G is a map from C to D. So just G belongs to Hom CD, so it is carried out by psi star to a map G psi, which is a model homomorphism from B to D. So that is, it is an element of Hom BD, such that this G is carried out to this map G psi by psi star, i.e. psi star of G is same as G psi. This means that given any sequence of modules and homomorphisms like this, A to B, B to C, so we have phi here and psi here, this sequence induces a sequence like this: Hom AD, Hom BD and Hom CD. but the arrows are reversed. So we have seen that if we fix module at the second place, then these arrows are reversed. However, if this module is fixed at the first place, then these arrows are preserved. I mean, their directions are preserved. Now let us do a result here. So this is our proposition. So it states that for any R module D and an exact sequence, suppose let D be any R module. So this is given to be an R module, and let 0 goes to A goes to B, B goes to C, and C goes to 0. So here we have map F, or let us write this map as phi and C. So if D is any R module, and let this be an exact sequence of R modules, then this sequence induces, then this sequence induces a sequence zero goes into Hom DA, this goes to Hom DB and Hom DC. So these are our modules. So this is map phi star, this is psi star. So we have to prove this sequence induces this sequence. So one should observe here that 0 is not coming out of this module over here, but 0 is going in. Now since 0 is going in, we have to prove phi star is injective, and then we have to prove this sequence is exact here, i.e. kernel of phi star is equal to image of psi star. That is what we have to prove. So first of all, we have to prove it is exact here, i.e. we have to prove image of this map, kernel of this image of this map is kernel of this map. And that is same as to prove kernel of phi star is singleton, i.e. that is same as to prove phi star is injective. So clearly phi star is injective because for if we take this map F here to be equal to 0, we have to prove F is 0, where in this F, so this F has to be an element here. So F being an element here means F is a module homomorphism from D to A. So where F is in Hom DA. Now if phi star F is 0, then by definition of phi star F is same as phi F, as we have mentioned earlier. So then phi of F is 0. This is the definition of phi star. Now phi is this map here from A to B, and since 0 is going in, that means phi is injective. Now if phi is injective, then phi of x equal to 0 implies x is equal to 0 because phi is injective. Similarly, phi of f equal to 0 means f is 0 because phi is injective. So this implies f is 0. Now if f is 0, that means phi star is injective. Then phi of f is 0. Let us write down the reason here. This implies phi star f is 0 since phi is injective. Hence phi star is injective. Now we have to prove here now we have to prove this sequence is exact here, i.e. we have to prove image of phi star is same as kernel of phi star. Now what we do, we prove these two containments, i.e. image of phi star is contained in kernel of psi star and this containment. But among these two containments, one is trivial. Let us look which one. Now psi star, phi star, this composition makes sense here because this sequence goes like this. First we have to operate phi star, then psi star. So by definition this is same as psi phi star, but the given sequence is exact. So that means so if this is exact here, this means image of phi is same as kernel of psi. Now if now we have to prove, so this implies so let x belongs to image of phi, or let x belongs to suppose b. Therefore psi phi of x, this is same as psi of phi x. Now phi x is in image of phi, but image of phi is same as kernel of psi. That means phi of x is in kernel of psi. So this means this is 0. Now since x was chosen arbitrarily, this means psi phi is everywhere 0. So here this psi phi is 0. So this is 0. Now if this is the case, this means image of phi star is contained in kernel of psi star. So this is 0. Now if this is the 0, this means psi star phi star of x is 0. Let us write down here f. This is 0 everywhere. So if this is the case, that means psi star of phi star of f is 0. Now psi star phi star of f is in image of phi star. So psi star when operated on image of phi star, this is 0. That means image of phi star is contained in kernel of psi star. So this is, we do not need to write this down here. So this is just a comment, a side note here. So this means, this implies image of phi star is contained in kernel of psi star. Now let us prove the reverse containment. Now to prove reverse containment, we will choose any element here arbitrarily, and we will prove that element is in this set. Now let beta be an element in kernel of psi star. Now beta being element of kernel of psi star, that means beta is in this set. That means beta is a modular homomorphism from D to B. If this is the case, then psi star of beta will be 0, because beta is in kernel of psi star. So psi star of beta is 0. But by definition, psi star beta equal to 0. Psi star beta is same as psi beta. This means psi beta is 0. That means beta is in kernel of this implies beta belongs to kernel of psi, which is same as image of phi, because our given sequence is exact. So this is same as image of phi. Or one can write over here so this is not necessary to write here. Now let us pick. So we have this module D here, this is module A, module B, and module C. This is phi, this is psi. Now these are the module homomorphism which are coming out of D. Now let us pick some element, say x and D. Let x be an element in D. Since beta is in kernel of psi star, so beta is actually an isomorphism, a module homomorphism from D to B. So then psi beta of x is same as psi beta of x, but psi beta is 0, so this is 0. So therefore this beta of x, this is in kernel of psi, which is same as image of phi. Now this is the crucial point here. So we have, so if beta x is an image of phi, that means there now image of phi is here in B. So that means there is some element, say y in A, such that phi of y is that element, i.e. beta of x, because beta of x is an image of phi. So hence there exists some y in B such that this phi of y is beta of x. Now let us see what we did here. So we chose some element x here and we got an element y here. That means there is some map from D to A. Now we have to exhibit that map. That means by choosing an element x in delta, we get an element y in A, which are related by this relation here, which are i.e. phi of y is beta of x. So this defines a map, say alpha from D to A, such that alpha of x is this element y. Now we have to exhibit this alpha. We have to cook up such alpha. Now one should note here phi is injective because 0 is going inside, so this phi is injective. Now phi from A to B being injective, so one can note that phi of A is isomorphic to A. Let us note this module phi of A by M. Let M be the module phi of A. So if M is such module, so we have therefore phi inverse from M to A is actually inverse of phi. I mean, it is an isomorphism because phi from M to A is injective. Now M is simply image of phi, so that means phi inverse is bijective. So this is inverse of phi. Now let us look here. Now image of beta, this is contained in kernel of psi. Actually they are equal, so if they are equal, I mean image of beta is contained in kernel of psi. This can be seen here. Beta of x is in kernel of psi. That means image of beta is contained in kernel of psi. So this follows from this point. But this kernel of psi is actually equal to image of phi, which is M. That means we have a composition map. Therefore we have a composition map phi inverse beta. Now this beta is actually a map from D to B, because this beta is in kernel of psi star, and kernel of psi star is contained in Hom dB. So one can look over here, kernel of psi star is contained in Hom dB. So this beta is actually a map from D to B. but over here B we have this image of phi. So this is beta from D to image of phi, from image of phi to, which is actually equal to M. From M we have a map B in phi inverse from M to A. So this goes to A via phi inverse. So this is the map which goes from D to A such that phi this alpha of x is y. So this is actually a map from D to A. Now what it does, it takes, so if we take this element phi of x, beta of, like this, phi inverse of beta of x, this is same as phi inverse of beta of x, this is same as y, because y is same as phi inverse beta of x. So this is the map we were looking at. So this is our map alpha. So this alpha is the map which takes the arbitrarily chosen element x here to the element y here. This implies that phi of alpha is beta. Phi of alpha is beta. Just take both sides phi, we get phi of alpha is beta. Or this beta, this means this beta is in image of, sorry, this means phi star of alpha is beta, or beta is in image of phi star. Hence we are done. We chose this beta here to be an element of kernel of psi star, and we end up with beta is in image of psi star. This implies this kernel of psi star is contained in image of phi star. Hence we are done, because we have already shown here that this containment is true, hence they are equal. So this proves. So one can note here, if 0 is coming out here, that means psi star is surjective, but it is not necessary, because if we look at this exact sequence, so this is an example. In above result, psi star need not be surjective, because let us look at this exact sequence. So 0 goes into 2z, 2z goes into z, and z goes into z or 2z. So these are, this is the Euclidean map and this is the canonical map, and this goes to 0. So this is an exact sequence here. Now let us choose our module D to be Z itself. So this is module A here, this is module B, this is module C. So take D to be equal to Z. So this exact sequence induces this exact sequence. So 0 goes to Hom 2Z, sorry, Hom Z, I mean take D to be this module. So this is 2Z, Z, this goes into home, this is 2Z here, this is home, Z mod 2Z, Z, this is home, Z mod 2Z, Z mod 2Z. So this is phi here, phi star, this is psi star. So one should look here that this psi star is non-surjective, because from, if we look at this set home Z mod 2Z to Z, we just have only one element. I mean from Z mod 2Z to Z there exists only one module homomorphism, that is a zero homomorphism. So it is size is just 1. Now if we look at this set here, home Z mod 2Z, Z mod 2Z, so we have two module homomorphisms from Z mod 2Z to Z mod 2Z. One is the identity homomorphism and other is a zero homomorphism. So its size is 2. So we cannot have a surjective map from a set having size less than to the set I mean we cannot have a map F from a set A to set B such that F is surjective and size of A is less than size of size of A is less than size of B. So we cannot have a surjection in that case.